Okay, let's get my stopwatch going. All right. So, this is supposedly Valentine's Day. I lost track of time, and so now it is the 15th. But hopefully, I'll get a few of these lectures together, or the lectures that I need to, so we can move forward. I'm going to keep these a little shorter than the full 50 minutes because honestly, I'm lacking a bit of motivation, but also there's quite a bit of information here and don't want to start down a path and confuse anybody and just barrel down a lot of information, because I know if this was in class, there would be some questions, which would obviously slow us down a little bit and hopefully keep everyone on the same page. So, as we discussed on Friday, we kind of started this new section of information about energy and variations. And the motivation here is essentially when we start devising more finite elements, the mechanics-based methods that we did with the bar element to date are very limited in their ability to develop equations for more complex elements. Plates is a huge one. Some of the other beam elements, we're going to go through a bar and a beam element derivation through the energy method, so you kind of see, hopefully we'll get the same result as we did with the bar element, but you'll see kind of the derivation techniques for the beam element as well. So obviously motivation is to really try and develop a means of bringing, a solution, obtaining a solution to more complex elements, okay? More degrees of freedom, more complex field functions and what have you. So, kind of talking about this energy refresher, right? We have conservation of energy as long as there's no energy lost to the system. We have this potential versus kinetic. This idea of energy, right, is the capacity to do work, where work is force times distance, right? That we discussed, there's a couple different branches of mechanics, right? There's vectoral mechanics, which is really what you guys are used to. And then there's this analytical mechanics branch, which was essentially developed by Gottfried Leibniz, who really came up with, instead of having vectors, right, forces, momentum, he replaced it with two scalars. So we have kind of the work of the force and then our living force, right? The vis viva, which is our kinetic energy that he devised as a method of quantifying kind of this branch of mechanics. So we have conservation of energy that we use, and then we have this principle of least action, right? So if we had two points of known position and velocity at two different times, and we know that the particle, then we know the position of the particle at some other time, right, t2, the path that particle could take could be any number of them. And once we assume that we knew a path, right, we could define both potential and kinetic energy of the particle as we went from, say, point 1 to point 2. So at any point along the path, when we calculate this living force, right, or kinetic energy, we can come up with this integral, which is the kinetic energy along the path, which would become the action of our particle, right? And the principle of least action states that the actual path taken by the particle is going to minimize this action or make it stationary, right? And the nature likes its least potential, really. So in the calculation of variations, right, we have this functional, right, or a function of a function, or really is an integral expression that implicitly contains, right, a differential equation for a particular problem. Well, in our case, if we were taking the integral over the path of this particle and its its kinetic energy, right, this vis viva or living force, that would be a functional. And variational calculus allows us to minimize a functional. to minimize is to find the minimum, right? We set the first variation of S, in this case is what we call the action, to 0. So we have the variation of S equals 0. And Euler and Lagrange, right, both mathematicians, they both independently found that the first variation is the solution to a differential equation, right? The partial of f with respect to y minus the derivative of the partial of f with respect to the derivative of y with respect to x equals 0. And that's how you find the extrema, or our optimum path. And as I mentioned, this was kind of funny because a lot of mathematicians, when I was doing a little background on all of this, pulling these notes together, a lot of the nerds out there really enjoy this equation and essentially calling it mathematical poetry. So we're going to start an example. Essentially, the idea here is to just kind of use variational calculus. And how could we use it? Well, we have 2 points known in space, right? Have an x of a y sub a, and an x of b and a y sub b. And we want to prove that the shortest distance between these 2 points is a straight line, right? And we could consider any of these possible paths. And that's what variational calculus does is, right, we're taking we're minimizing an integral, right? So a surface or a path. So if you minimize those, obviously we're going to make the smallest. And in doing so, if we want to minimize the path between 2 points, we would then have the shortest distance. So we need to know the length of the path in terms of the function, right? Y sub x. So I'm saying that y is dependent on x, and that defines the path. And so if we start by looking at, all right, how do we define this path? We would have some sort of differential length of the path, right, dl. Over that length, we would have some rise, right, with some change in y and some change in x. Okay, so if we blew that little triangle and enlarged it, blew it up here, right? So as we move from A to B, we're going along the path there, right? If we went some differential length or small length of L, we would have a component in the X and the Y. And so if we use Pythagorean theorem here, we'd say dl squared equals dx squared plus dy squared. Well, if we pull a dx out, we can say dx squared multiplied by 1 plus, right? Now we got to divide dy by dx. We're going to square that whole thing, right? And then we get that equal to dl squared. Well, we want to know what dl is in terms of dx. Well, dl equals the square root of 1 plus the derivative of y with respect to x squared dx, right? Well, the length, right, if we were going to come up with the length of the line that goes between A and B, right, that would just be the integral from x of A to x of B, right, definite integral dl, right? Well, we know dl is a function of y sub x, right? The derivative of y sub x and x. So we get now that the length equals the integral from x of a to x of b, the square root of 1 plus y bar squared dx. Right? And this is our functional, right? This is what we really want to minimize. Right? So we want to find y sub x that gives a minimum value of L. Well, in order to do that, as we've already looked at, we want to set first variation of L to 0, right? First variation of L to 0. That is variational calculus. That's how we minimize a functional, right? So if we set the first variation of L equal to 0, and we look at Euler and Lagrange's solution, right? D dx partial of f partial of y minus partial of f partial of y equals 0. All right, so that's our solution to our functional. Well, our functional in this case, right, is our square root of 1 plus y bar squared. Right. And as you can tell here, right, f is not a function of y. Right? So if we took the derivative or partial up here, right, if we took the partial of f with respect to y, you're going to get 0. So that goes away. Right? So we just have now our d dx partial of f partial of y bar, which is our derivative, equals 0. Well, if we integrate each side, right, we need to get rid of that d dx. We're going to integrate each side. I'm going to say now the partial of f with respect to the derivative of y. Get some sort of constant, right? C. It's based on integrating, right? Constant of integration. We're going to integrate both sides. So we get rid of the d dx, but now we get a constant. Now we want to take the derivative, right? So we're going to say partial of f with respect to y bar equals, well, that's the partial of our functional 1 plus y bar squared all over partial of y bar. Well, that's really equal to y bar over square root of 1 plus y bar squared. That's all going to be equal to a constant. Right? Those are rules of integration there. With respect to powers. So now we can solve for y bar. Well, we get y bar equals c, right, or our constant over the square root of 1 minus c squared. Well, that means really this whole thing is a constant. Right? So when we think about it now, right, what function has a constant first derivative? Right? What constant has a what function has a constant first derivative? Right. This is when I would call on you guys normally, but since I am not there, if we had a function with respect to y, right, and a constant first derivative, well, that means that it's going to have some linear, right, linear function of x. So we could say a line in our case, right, the equation of a line, or y equals cx plus b, right? If you took the derivative of that, we're going to just get a constant. So that proves to us, right, that the shortest distance between 2 points, or the minimization of this functional, which was described by our square root of 1 plus the derivative of y with respect to x squared. You minimize that, right? We need to get a constant. Well, in order to get a constant, the first derivative of a constant, or the first derivative yielding a constant, right, of a function is a linear function with respect to x. And so we get our line. So the shortest distance between points is our linear line or a straight line, okay? Pretty interesting. So that's our example. Philosophically, if we look at variational calculus, right, there's some interesting things here, right, over the years. So don't miss the unique approach used in variational analytical mechanics, right? There's a mathematician once said, so indeed, the idea of enlarging reality by including tentative possibilities and then selecting one of these by the condition that it minimizes a certain quantity seems to bring a purpose to the flow of natural events, right? What does this mean? Well, essentially saying, right, variational calculus gives us this means of looking at things that maybe appear to be in chaos, right? But if we look at it in a means of looking at all possible paths of a particle, for instance, okay, or flow of water or something like that, right? We're going to look at all of them, and if we use the principle of least action, right, we can essentially determine that there is less randomness. Well, in the 17th and 18th centuries, there was a big push, right? We wanted to find that purpose or order or reason. In nature. Things were so unknown, we felt like they needed to be known. Well, this actually, as we progressed in society, it really kind of fell out of favor. In the 1800s, right, or 19th century. Right. And it's kind of come and gone. Right? So if we go back to a review, right, of our energy and variations, our motivation here is that energy and variational techniques provide a powerful method for deriving a lot of finite elements in the finite element analysis method. So deriving many elements in FEA. That's the tool, right? We're going to use this as a tool so that we can get more elements, derive more elements to hopefully provide solutions to a wider range of problems, right? So when we talk about energy, we're talking about potential energy, kinetic, right? This is our, vis viva, right? Or our living force. We have work, right? Force times distance. We have conservation of energy that we use, right? With our history, right, we had the first branch. This is vectoral mechanics, right? This was Newton. We're all familiar with our physics classes, right? Vectors. We have our force and more momentum. Our second branch, well, that is our variational. Well, this is our Leibniz, Euler, Lagrange, Right? These are scalars of work and energy. So we have the capacity to do work, and then we have the work done, right? And we're going to talk about that here in a little bit. So we have the principle of least action. Well, that is the actual path of the particle will minimize the action. Right? Path of least resistance, if you will. We need to use that, and we will continue to use that. Right? So we have this calculus of variations. We have ordinary calculus that we're all used to, where in ordinary calculus, right, it gives us this means of how to minimize a function. Well, now variational calculus allows us and also shows us how to minimize an integral. Right? And that is, it tells us how to minimize, say, paths or surfaces, right? For example, right? So how is this helpful in finite elements? Well, as you can imagine, we have these discretized models that are made up of tons of these elements, and these elements have to have some sort of assumed, right, surface or shape. We get our, sorry, I got something. We have this really, in some cases, elaborate assumed field function, right? Field variable function across the surface. Well, we know that because of the principle of least action, we're going to talk about the principle of total stationary potential energy, right? And our principle of virtual work, right? That in equilibrium, things go to zero. So we want to minimize these functions, and a lot of times these functions are a surface, like I said, or a path, which are defined by an integral. And so variational calculus allows us a means of coming up with a solution to those problems. Right? So ordinary, as I mentioned, right, this is a function, say y sub x. Variational, it's a functional, right? Which could be a function that is really a function of the derivative of a function, right? So it's a kind of a function of a function. Right? Philosophy, as I mentioned, right, they have a different feel, right? Analytical mechanics is a bit different, right? We talk about scalars and energy and work. And because of that, it's kind of gone in and out of service or in and out of style over the years. But it's a very powerful tool in the finite element analysis method, okay? All right, so that's energy and variations. We're going to jump into our second note sheet here, or 4B, right? Second part of energy and variations. Well, we have this principle of virtual work, right? So what's it saying is a particle is in equilibrium if and only if the work done by all of the forces acting on the particle is zero when the particle travels through a virtual displacement. Well, let's look at this more visually here, right? So let's consider a particle in equilibrium, right? So if we had a particle, it's our particle, we have all of these forces. F1, F2, F3, F4, and if we were looking at, right, this particle, all the forces acting on a particle is zero when the particle travels through a virtual displacement, right? So the work done by all of the forces acting on the particle is zero. So we have some sort of delta U, or some small change in displacement. We have, right, the angle over which all of our forces are acting with respect to that displacement. Right? We know in equilibrium, right, the sum of the forces equals zero. Right? What does that mean? Well, that also means that right, if it's in equilibrium, then the work done by all those forces, if we were to move, right, displace that particle, some delta, would also be zero, right? So imagine the particle undergoes a virtual displacement, delta U. The work done by the system of forces is, well, that is force times distance, right? So our delta U creates a change in work, right? And if we were to sum from our first particle to our nth particle of the force of that on that particle, right? F1, for instance, its contribution in the direction of the displacement would be cosine, right, of that angle, finally times delta U. That would give us our work, right? Because work is force times distance. Right, so we can move this out front. So we get delta U equals summation I equals 1 to n f sub I cosine theta sub I. Whoa, I don't know why I did equals delta U. Just move the delta U out front. What does that mean? Well, this is zero when in equilibrium. Right? It's the same displacement for that particle regardless of the force that's acting. And so in order to have all of the work going to zero, well, that means the forces, right, all the components of the forces in that direction need to be zero. Right? So that way our change in work equals zero. Right? Or delta W equals zero. So that's our individual particle. Well, if we looked at a system of particles under internal and external equilibrium, let's start by drawing a little system here. The system might have, I can look at it by having a series of, right, stiffnesses between particles, right? These would be springs. I don't know why I deleted that. And these springs, right, would have internal forces in them. We'd also have, external forces acting on these particles, potentially, right? So these are external. So if we consider this system of particles, they have external forces and internal forces. So if we let this entire system now go through some displacement, virtual displacement, right, delta U. Well, from the previous, as we saw, right, from the previous, delta work of the jth particle, right, equals 0 if we're in equilibrium, right? If in equilibrium. This is our jth particle. Therefore, right, so for each of the particles undergoing that, virtual displacement delta U, well, each of those particles, right, could be in equilibrium like we did our individual particle, right? So all the forces acting on that particle, right? The work done by the system of forces would be whatever forces are acting on that particle, whether it's internal or external, right? And whichever direction that virtual displacement was, we could get a work done by those forces on that particle. If we look at the system level, right, because of we can look at it at the particle level, at the system level now becomes delta W of the system equals the summation J equals 1 to N, right, of each of the particle is really just a summation of each of the particles' work done. So we can separate this out, right? So this is all of the work done. Well, as we can tell here with our system, the springs, right, the interconnection between our particles, there's forces associated with that, right? And then there's external forces associated with external, right, applied loads and things. So if we can separate this and we can divide internal and external, so we can get that the change in work external, right, or the virtual work, of external forces and the virtual work of internal forces right? Well, both of those added together, if the whole system needs to be to 0, if we look at each particle individually, well, obviously if we add or we split these up into the change in the external plus the change in the internal, that also must be 0, right? The work done on the system. And if we make a note here, just to make a note regarding the assumptions we made, well, no, we made no assumptions here about the nature of the system, right? The principal virtual work, it's valid for linear, nonlinear, elastic, plastic behavior, right? This principle that right? A particle is in equilibrium if and only if the work done by all of the forces acting on the particle is zero when the particle travels through a virtual displacement, right? So if that particle moves, right, the work done by all the forces on that particle, whether they're internal or external, right, all of them summed together must equal zero. Right? If there's an imbalance, then that means it's not in equilibrium, right? So we could just say no assumptions made about the nature of the system. Right. Principle of virtual work, PVW, is really valid for our linear systems, our nonlinear systems, elastic and plastic behavior, are all valid with this principle. Okay. Well, with that, I am going to stop. We're going to do another one, okay? Another day here. I'll get it uploaded. Hopefully all of that makes sense, and you guys are having a great week.